Finally, are you ready? Okay, probably not, so let's review the definition of the derivative. From the slope of secant line, we get this notation, f of b minus f of a over b minus a, and then taking a limit, we get the derivative. By substituting b as a plus h and b minus a consequently as h, we get this equivalent notation. And this quantity is called Newton quotient, and this is probably the easiest way to calculate the derivative directly from the definition. And let's go over to a problem that we really have to do that. And here's one such problem. And for reminder, let me write down the definition of the derivative right here. Well, looks like it's not really necessary. I already wrote down here and then gave you a guideline. And there's a reason that I am using the piecewise defined function here in this example. In next chapter, we're going to learn a variety of different techniques to calculate the derivative functions in much easier fashion, even for much more complicated functions. So using this Newton quotient is not going to be appealing to a lot of students if I use standard functions. For piecewise defined functions, well, all those techniques we do in chapter 3 will break down, so we'll really stop with this. So let's go ahead and do the computation with the Newton quotient. So what we need to do is find out this limit. So find out the left hand side limit, h is going to 0 minus, and the right hand side limit, h is going to 0 plus, and then calculate those. And let's see if those two are the same. Consequently, we have the derivative. It'll turn out to be the same, by the way, if I remember correctly. Okay, here we go. Let's find out the left-hand side slope, and we can do something like this. Looks like I'd better expand the font a little bit. I hope that's better. Okay, f of 1 plus h minus f of 1 over h. F of 1 plus h is basically the same as plugging 1 plus h in place of x in the definition. The problem is, which line do I use? Well, h is a little bit less than 0, so 1 plus h is a little bit less than 1, so we have to use the first line, this one. So plug in 1 plus h in place of x for those, and we get this part. 1 plus h squared plus 1 plus h minus 1. Now what is f of 1? That's right here. X equals to 1 is right here, so you have to plug in x equal to 1 to these. So 1 squared plus 1 minus 1, that's going to turn out to be 1, by the way. So now that we have this Newton quotient, let's calculate it. Break up the parentheses by complete square method, and then do some algebraic manipulation, and further algebraic manipulation, and we end up with 3 plus h. What does that mean? The limit of this Newton quotient is the same as limit of 3 plus h. And that's a trivial limit, 3 plus 0, so we have 3. And this tells me the left-hand side slope of this piecewise defined function has slope 3. Okay, now let's go ahead to the right-hand side slope. We have to okay, so we'll have to use the second line this time, because 1 plus h is going to be a little bit bigger than 1 this time. So 1 plus h is a little bit bigger than 1 because the h is bigger than 1, so we have to use the second line. Oh, okay, I'm having a little bit hard time highlighting the right place. So okay, the second line here, and replacing x by 1 plus h, we get sine of 1 plus h minus 1, like that. And then when x is equal to 1, we have to use this one, x is equal to 1, so it's going to be the first line again. And then let's simplify. Inside sine, we have 1 plus h minus 1, so we just have sine of h. And then simplify, what do you get? Sine 3 times sine of h over h. Now, haven't we seen this quantity before? Well, I hope you remember this from the limit computation, the previous lesson. This Newton quotient is the same as 3 times limit of this sine of h over h. And this limit, sine of h over h, is 1. So what do you get? 3 times 1, we have 3. Consequently, what we have? Left-hand side limit, or left-hand side derivative we calculated was 3. That was part A. And then part B gave us 3 for the right-hand side slope. And these two are the same, so the limit exists. So limit exists, so the derivative exists, because derivative is given by this limit. And what do you get? The derivative is the common value, 3. Let's verify that with this picture. Here it is. Left-hand side is this blue, right-hand side is this red, and this is piecewise defined function. And let's go back to standard font size so that I can see everything. Okay, and then right-hand side derivative and left-hand side derivative are the same, and the tangent line is visualized into this purple dotted line, and that slope is 3. So compare this kind of smoothly joined picture and this kind of wacky picture right over here. You see the difference. This is a cusp, so no derivative, and this one has derivative. We have this nice spline. Okay, that was challenging, but yes, this was challenging, but still this is well within Calculus 1 curriculum. And if I write this kind of problem, it's gonna be upper level problem, yes, but definitely it is okay. Let's talk about a problem that is specifically designed for exceptionally high level students, like mathematics majors or anyway, here you go. Let's consider kind of like continuity condition problem. Well, let's consider differentiability condition. We have a function defined piecewise with a parameter a, and then let's find out appropriate a value that will make this function differentiable. How do we do that? Well, what we need to do is to find out the left-hand side slope, the left-hand side limit of the Newton quotient, and the right-hand side limit of that Newton quotient, and then set them equal. And if we set them equal, we are going to get an equation, and that's going to be an equation of a. That's how we can determine a. By the way, before starting this problem, please note that this function is always continuous. If you plug in x equals to a times 1 squared plus 1 minus a, so we're going to get just 1. If you plug in x equals 1 to the second line, we have 1 minus a times sine of 1 minus 1, so sine of 0. So again, we are going to get just 1. 1 minus 0, so it's 1. So at least continuity is just trivial. Differentiability, of course, is going to be a challenge. Let's go. Let's calculate the left-hand side derivative. Maybe we should increase the font again. We have to look at this Newton quotient a little bit more carefully. Okay, here we go. Get the Newton quotient, a plus h minus f of a over that. And we have to replace x by 1 plus h in that definition. And left-hand side derivative, so x is a little bit less than 1, so we have to use the first line. So we did that right over here. And then we have to plug in x equals to 1, again the first line, to get the function value. Equality is over here, so we have to use this one. And we end up with, well, a plus 1 minus a. And here, breaking up this parentheses with complete square and so on, we get this manipulation. And then some further computation, taking some like terms together, we have something like that. Some further simplification, we have h squared plus 2ah plus h, and we have a cancellation. Everything has h. So cancelling out those h, what do we have? We have h plus 2a plus 1, and denominator is gone. Finally, we ended up with a trivial limit. We can plug in h equal to 0 at any time. Oh, excuse me, not at any time. After this simplification, after this denominator is gone, we can do it. Okay, plug in, then we get 2a plus 1. So that's the conclusion. The left-hand side derivative turned out to be 2a plus 1. Okay, and then let's calculate the right-hand side derivative. Let's use the second line this time, because 1 plus h is going to be a little bit bigger than 1 because the h is a little bit bigger than 0. So plug in 1 plus h in place of x, we have this. And then for f of 1, again, we have to use the same computation as before. Equality is for first line. We have 1 plus h minus 1 inside is sine, so we have sine of h as before. And further simplification, what do you have? Negative a times sine of h over h. And what is sine of h over h? I hope everybody still remembers. That's limit is 1. So what do we get? The right-hand side derivative turned out to be negative a. So left-hand side derivative turned out to be 2a plus 1. Right-hand side derivative turned out to be negative a. So setting those equal, we have 2a plus 1 equal to negative a. And that's an easy equation now. A is negative 1/3. So that's when this function is differentiable at x equals to 1. Consequently, it is differentiable everywhere, by the way. When x is strictly less than 1, we have quadratic function. And then when x is greater than 1, we have the sine function. So everything is good. The only possible bad point was x equals to 1. But by this limit computation with this Newton quotient, we took care of that. By the way, you can plug into either right-hand side or left-hand side, but if you plug into right-hand side, as I did, it'll turn out, the derivative will turn out to be 1/3. If you plug into left-hand side, again, it should be the same thing because we set them equal. Okay, derivative is 1/3, and derivative is 1/3, and then that's possible when a equals a negative 1/3. And that was the conclusion. And let's visualize that. Let's justify that with this visualization. And here it is. I hope this visualization works. Okay. Something is not right with this Mathematica program. Okay, so Okay, I give up. I'm sorry I wasn't able to visualize this animation because it was rather too complicated a program. I mean, it's kind of like this, and then somewhere down the road something is not completely right. Okay, I think I fixed this program, and let's watch this animation. Okay, the blue part and red part. Okay, as it moves around, when a value hits 1/3, we have smooth, and this red dotted and blue dotted coincide with this purple, and that's when we have differentiability. Otherwise, this cusp is developing and getting more and more pointy.